Okay. So now that we all have gone through this exercise of reflectivity, so the question must be coming to your mind that when can we make sure that we got the best model, or if we get the best model, how can we say that about our parameters what we are getting? So ultimately the question is, what's the confidence of what do we have in confidence in terms of parameters? So that's what this error analysis is all about. So getting the confidence interval of parameters. So I will try to explain it in terms of in terms of an example. But here the idea is, when we did this data fitting, what we got is the parameters like rho, d, sigma, as a function of different layers. And then what we tried to do is minimize the chi-square and try to get some values of rho, d, and sigma compared to minimum chi-square. So the question is, what are the error bars from the for the rho, d, sigma values what we are getting from the data fitting, and what does this error bar or confidence of interval means, and then how do we determine it? So I will show you that, and then I will show you with a demo like how to get this kind of error bars, and then we'll have some tiny exercise for you guys so that you can get the error bars for the parameters yourself. So let's dive into it. So I will try to explain it because reflectivity curve is a very complex curve. So I will try to explain the error bars with a very simple model, which I'm showing it to you here, which is basically a linear fit model. So here you get a linear data, and as you can see, the data has some error bars, which certainly shows that there is an underlying distribution of data values. So there is always a distribution from where you get the data values out. And when you do experiment, you get one set of distribution. If you repeat the experiment, you can get another set of data points, but which will follow the same distribution. So what you will get is a collection. When you fit it, you get a collection of parameters. Like here, I'm showing it. The minimum chi-square gives you for this particular data shown by this blue line, which will give you the C minimum and M minimum, the slope and the intercepts, the intercept and the slope, by minimizing the chi-square. Now you can say that I can get another set of parameters CM1 and M1, which can give you another chi-square. So in this way, you can generate a lot of chi-square values corresponding to C and corresponding to different values of C and M. And then what gives you the criteria that this is the fit I can get? And from this distribution of parameter values, I can say that with confidence that with a certain confidence that my parameter will be between some range, and that range belongs to the that range is basically what we call confidence interval of that parameter, or error bar on that parameter corresponding to the data we have obtained. So when we talk about chi-square has an underlying distribution which is independent of any model. So like here, this is the distribution, theoretical distribution, which comes out of chi-square. And when you try to fit it with a particular data, this chi-square, what we get from the data, will follow this kind of distribution. And as you can see, always the chi-square minimum follows the kind of distribution in a way like the chi-square minimum will be the peak of this distribution. And below this peak, it will follow the curve which is proportional to chi-square, and above this, it will follow the curve which is basically the exponential decay with respect to chi-square. And as for in this example, I have this chi-square corresponding to C1 M1. I can plot the same chi-square value in this plot and see the probability of getting that. So in this way, you can get two other, or you can get this kind of chi-square corresponding to different kind of confidence intervals, which we show it as 95%, 68%. So 68% is generally belongs to the 1 sigma of this, distribution, and 95% corresponds to the 2 sigma of the distribution. So depending on how we are reporting the error bars on the parameters, we have to mention which kind of confidence interval we are referring it to. Either it is 95% or 2 sigma, or 68% 1 sigma. So the question now is, whenever I'm plotting this M versus C as a chi-square plot here, it shows you that first of all, the chi-square minimum will be the minimum chi-square, and which is the darkest region here, and the values corresponding to chi-square 1 and here corresponds to these 2 positions here. So ideally, if you plot C versus chi-square versus all the parameters, you will see some sort of plot like this. So here we have 2 parameters, that's why it is a 2-dimensional plot. If you have like multiple parameters, it will be that much dimensional plot you have. So in order to get this kind of confidence interval, you need to generate this kind of chi-square versus parameter plots. So that is one thing you have to generate. Another thing you have to get is what is the chi-square corresponding to this confidence interval, like 95%, 68%, how to get that kind of chi-square value which corresponds to this. And that comes out from this distribution itself, which I will show it in the later slide. So we need to determine 2 things, like chi-square corresponding to the confidence interval which we want, and the chi-square versus parameter plots like this. So these are the 2 things which we need to have to get the error bars. So in order to get the chi-square values, there is a well-documented thing which is very well explained in Bevington and Robinson. This is the gospel for data reduction and error analysis theory. So if you want to go more into this, I will suggest you to go to this book and go through this section of error analysis. So the way it does it is, you have this chi-square distribution as I have shown you. In this, there is a region called, there is a concept called p-value. P-value is basically the integration of this region, which is corresponding to the chi-square value confidence interval you want for this. For example, here I want 95% confidence interval. So I integrate this region, and I get a p-value which will be like C minus 95%. That will be like 0.05. 0.05. So here it gives you a table, which is a chi-square distribution table, which gives you p-value and degrees of freedom. So degrees of freedom is basically another parameter which is very important for getting a distribution, and which I didn't explain it in the earlier slide, but basically it is the number of data points minus the number of fitting parameters, here you have. Go to that slide here. So basically this number of data points and number of parameters here is 2. For this particular example, the degrees of freedom is 8. So once you have this degrees of freedom, then you get this p-value from the table, which is tabulated here. You can calculate it also from this, by integrating this chi-square distribution. So once you get the p-value for 95%, we can get to 0.05, and we have 8 parameters here, so you can get the chi-square corresponding to this 8 parameter, which is like 1.932. So here the chi-square distribution table is normalized by the degrees of freedom. So really the chi-square should be like, you have to multiply this degrees of freedom with the value we are getting here. So in this case, the value will be like 8 multiplied by 1.932, which should be very close to around 15-16 chi-square value. So once you have this chi-square value, then the next thing you need to have is generating the chi-square versus parameter plots. So there are various ways of doing it. So first way which you can think of is doing a grid calculation. So you vary over all the CM and M values, calculate all the chi-square from the plot, from the chi-square from the data, comparing it with the simulation, and then you generate this kind of plot. But the disadvantage is, it can take hell lot of time, because here there are 2 parameters, so it will be easier. But if you suppose when you do reflectivity, error analysis, you will get multiple parameters to fit, and then this kind of approach will take a long time to calculate this chi-square versus parameter plot. So that's why we have we have two other ways of doing it. One is I will explain like chi-square distribution method using fix and fit, and another thing is Markov chain Monte Carlo, which is a kind of a smart way of doing it and uses statistics in the background to calculate the error bar. So I will so both of them are implemented in our software, and I will show you a demo by how to do this kind of calculations. So let's understand what this fix and fit chi-square distribution method is. So basically in fix and fit, what we do is we divide this chi-square, divide this parameter space. Like for instance, here we divide this C into equidistant values. So we know exactly the C values where we want to get the chi-square, and then fit it in terms of M. So basically you get this kind of individual points like this, not the full parameter space, but individual points like this. And then you plot the chi-square versus C. And similarly, you can do the other way around, and you can generate this chi-square versus M. And as we already have calculated chi-square 95 from the table, you can plot it here and try to see where they are intersecting. And you get the intersection point, and you get this like negative, the confidence interval from this region to this region for C, and for M you get this for this region to this region for M. So here I'm showing it with an example, and I have written it for in general for any kind of parameter space. So the algorithm I have mentioned it for any kind of given parameter numbers. So this thing has been implemented in our software. And then I go to the next method, which is called Markov chain Monte Carlo. So this is based on some kind of Monte Carlo algorithm. But what we do is we start with a parameter set, which starts from the minimum chi-square, and then we randomly move around this parameter space. And when we move around this parameter space, we try to compare the chi-square in the existing point, and then when we move to the new point. And from that, we calculate an acceptance ratio. And when this acceptance ratio is compared with a random number generator between 0 and 1, we accept it if the acceptance ratio is more than that number, and if we reject it if it is less. So for instance, you can understand that this is the minimum chi-square, right? When we try to move out of it, the alpha value will be always less than 1. But as it is compared with a random number between 0 and 1, so there is a finite probability that you will accept it and or reject it. So in some cases you will accept it, and in some cases you will reject it, which I have marked at crossed here. And in this way, you run this thing for many steps, and you can then generate a plot like this, which will give you something like give you a distribution of chi-square in terms of parameters. And you have to keep doing it until you get the correlation between parameters close to 0, means like this. And once you, I will show you in the example how to do that, but once you achieve this state with this considerable number of steps, then you can use the statistics to get the number of get the error bars. For instance, you get this kind of plot, probability distribution plot from the analysis which you have done, and you integrate it along like one direction, like M, you get the error bars along C, and you integrate it along C, you integrate it along C, and then you get the error bar along M. The same approach like what we shown before. So these are the two different ways of getting the error bars, and I will show you now with a demo like how to do it in our software. So when we were fitting the data, we start Wave has shown you like fit the D15 RRF data, right? So I will use the same data set to go through the error bar analysis. Okay, let's stop here. Can you see the software?
Yes.
Okay. So let's add that file one more time. D50. Okay, now we have the data. We can fit it with this one layer model. So we can add another layer, which is about 15 streams, 0.4, and you fit this, all the parameters. You get a best fit. Once you have this best fit, then the options which will be available for confidence interval is these two, as I mentioned, chi-square distribution and MCMC. We'll see each of this individually. So then you select this and then calculate parameter error. Then it will open up a new window like this. And here you see all the parameters which for which you want to calculate. So by default, it has all the settings you need to do. But here the chi-square confidence interval I have mentioned here is 68%. You can choose 95% if you want. I will do it for 95%. And then do just calculate all. So it will calculate the error bars for all the fitting parameters one by one and show it. Okay. So it shows that the error bar for this thing has a maximum limit. So I will change it to, let's say 5. I'll do it again. Okay, so now as you can see, we have got the error bars here. This looks good. This thing we are on the edge, so maybe what we should do is increase this minimum maximum percentage a little bit more to get to this. So we can do it quickly. Just go to point, double it. And repeat it again. Yeah, this looks fine. So we got this error bars on individual parameters. You can see the error bars here, the positive, negative, and here also the parameter values and the left and right error bars. Also you can see. So that thing is done. You can save all the chi-square values, what we have calculated so far. You can save the parameter intervals. Let's say chi-square distribution method. And this thing is done. Then we can go switch the MCMC and do the calculation of this parameter interval again. So it will open up a different kind of window now. So also again, the settings are mainly done. What we need to do is, as I said, it's a random process. So you need to sample it over several parameter space. So that is basically, we need to run it for many times. So for instance, we'll do it for 1,000 steps. So it will take some time to do this. In the meantime, what I will do, I will reduce this. I will reduce it to 500 steps. But ideally, it should be done for. Okay. Okay, let's do it one more time. Fit it again. And calculate parameter error. And change it to 500. Yeah, I will show you the advantage of this method compared to the other one. Other method is faster, definitely. As you can see, that was much faster. But this will show you much more information than the other method. So line in the other method means the chi-square 95%. That's what you mean? I think that was.
I meant in the plot of the two parameters versus the chi. Like you look like you took a line through the curves of chi and disted along that line. So how was that chosen?
Oh, that was chosen from that probability distribution, as I mentioned. So you know the confidence interval which you want to measure. Like suppose 95% corresponding to a different line compared to 68%. So you get it from there and then get that intersection points from there. Okay, here we get, as soon as this is done, you get the parameter correlations. So this is the region where the parameters are kind of correlated compared to the minimum chi-square positions. So we have to, in order to get the statistics done, we have to neglect this region. So generally above, for this particular example, above 100, the data what you're getting is good. So that's where the MCMC burn means, like you neglect all these 100 data number of parameters which you generate here, and we want to do 95%. So the percentile will be 97.5, and then you get the confidence interval by calculating this, and then you get this kind of plot which gives you the probability distribution of chi-square. And from this plot, from the left and right, you get the error bars, and the confidence interval is also shown here. You can save them as you want, but before going to that, I want to show you a few important things here. So as you can see, this thing is very much symmetric, these two plots compared to this one. This is a little bit asymmetric and elongated. So what this plot means are, this plot are basically correlation between two parameters. So this plot shows correlation between d value and the rho value. This plot shows correlation between d value and sigma value. This plot shows correlation between rho value and sigma value. So as you can see, this plot shows that if you are a little bit away from this minimum chi-square, suppose you are going away like this, so if you have different rho value, which kind of like if you reduce the rho value, your sigma value has to reduce to get to minimum chi-square. So, but this is not true for these two parameters for this particular case. So the advantage of this method is it not only you are getting the chi-square, the error bars from for different parameters, but also the correlation between the parameters visually, which is very nice. And I will show you like when this correlation. So for this example, still you have correlation, but it is less compared to what I'm going to show you now. When we reduce the Q range for the fitting. So let's go there. I will save this parameters as well. For instance, I will save it as MCMC Dist. And another thing I want to show you is, but that I can show you later, but let's go to do the fitting with. So now we have fitted the whole range, whatever the data available, right? But suppose you don't have the whole range of data available. For instance, suppose you have only the experiment done up to 0.35. So you can choose it here, the fitting range 3.5, and you're assuming that your data above this is not available, for some instance. And then you fit the data, you get again some set of chi-square minimum, and gives you the chi-square minimum value for best fit parameters, and then you calculate it again with MCMC and do the same process. 100 steps. This will be quicker because we are using less data points now for fitting. Basically half of whatever time we took earlier. But now you will see how the data will be correlated in all this space, all the parameters. Okay, now again we can do the same thing. Now you see all the parameters become correlated. So what does this show? And also the error bars will increase. Yeah, the point is not the error bars here will increase, but the main thing is to show you that whenever you have a data, whenever you have a reflectivity data, you have to get the data as much as possible in Q. That will reduce the correlation between parameters, and you can get the parameters with more with the parameters with less correlations. That means the parameters are more reliable. Once you have correlated parameters, the parameters are not that reliable. That's the message of this. Like, you need to get the Q range as far as possible for the reflectivity data. Getting the experiment done in such a way that you get the Q range as far as possible. Okay, now let's go back to the talk. What I mentioned here is I showed you the chi-square distribution method. I showed you the MCMC method. I showed you how the Q range affects the confidence interval in terms of correlations. Basically, this is what I showed you. If the parameter correlation increases as you change the range of Q values for the fitting. Also, the confidence interval of parameter increases. So as the things getting correlated, the confidence interval also getting increased. So that means you are less certain about the parameters values you are providing as a fitting parameter. Okay, now what's the advantage of this disadvantage of both the parameters? So chi-square distribution, as I showed, compared to MCMC, it's much faster. But the disadvantage is there is no way you can get parameter correlation from this method. Also, if you compare the parameter error bars or confidence interval from these two methods, you get larger possible error bars from this compared to MCMC distribution. I will explain it to you this thing later, but before that, let me also tell you that For certain parameters where they are very highly correlated, this method may not even work, but this method, the MCMC method, will always work. So that's why MCMC method is much more powerful, but it takes, of course, it takes more time to calculate. But you will always get some kind of error bar from these parameters. So now to get to the answer, like why you get larger error bars from chi-square, comes from the fact that, as I mentioned you from this, what we are doing is, if I compare this method with MCMC, what we are doing is we are running along the maximum change in the parameters. When we are fitting the data in different spaces, we are going along this direction. But in MCMC method, we are integrating along this direction. This gives you a different distribution compared to whatever we get from chi-square method, chi-square distribution method, or fixed fit method. So that's why the error bars you obtain from fix and fit is larger than the error bar you get from MCMC method.